we're going to talk about related rates. So the idea here is that we have problems where we are trying to find the rate at which some quantity is changing by relating the quantity to other quantities. That is one variable changing related to changes in other variable or variables whose rates of changes are known. Okay, so here I have an example. This is an example of an inverted right circular cone, and suppose the water is being drained from the bottom of the cone. Suppose there's a tiny hole near the bottom here that drains the water out of. And for this situation, let's say we want to know the rate of change of volume over time. So what we're interested in is we want to know dV dt. Again, this is the rate of change of volume, WRTO with respect to time t. So notice here we have an outside variable t where it affects all three quantities here. It affects the volume, the height of the water, and the radius of the surface of the water that's inside the cone. Okay, so what we need here is actually an equation, and usually we get this equation from the geometry of the problem. So it's very important that we draw a sketch of the problems that we do in this section. Now, the volume here of a cone is going to be 1/3 pi r squared h. Let's say this is from geometry. Okay, suppose we take that to be a common knowledge. So notice the variable that I want to find the rate of change for is the volume, right? So to know the rate of change of volume, I need to know the rate of change of the radius. I need to know the rate of change of height. And all of these changes are with respect to time. So we're going to differentiate both sides of this equation with respect to time t. So our assumptions essentially are that volume is a function of time, so is the radius, and so is the height. Okay, so when we take the derivative, therefore, all of these derivatives, we have to do implicit differentiation. Okay, so to put more specific detail for the left side, the volume and the derivative of v, so if this is v prime is going to be the derivative of that. The derivative of v is just 1, right? It's like derivative of x. What is the derivative of x? It's just 1. So same thing, the derivative of v is 1, but then because v is a function of t, therefore we need to work the chain rule, and that's how you get dv dt. Okay, now continuing on the other side, well, pi over 3 is a constant multiple, so we take the pi over 3 out. Now let's work inside r squared times h. Here we're going to apply the product rule, right? And keep in mind r and h are both functions of t, so we do have to do chain rule when we take the derivatives. So let's begin with r squared times h. The derivative of r squared is 2r, correct? But then because of chain rule, because r is a function of t, we have dr dt times h. That's just derivative of first by second plus first times derivative of the second. The derivative of h is 1, and then of course we have dh dt. So notice all of these variables, all three variables, v, r, and h, because they are a function of time, we have to apply chain rule to them. And we just did our derivative. Okay, now we can kind of clean this up a little bit, not much because I don't have any numbers. We can create numbers and work this, but we'll see another example with numbers. This is just more general structure. So this is going to be 2r h times dr dt plus r squared dh dt. And there we go. So we don't have, again, a closed form of an answer with numbers because I didn't put numbers to it. Now we can find the rate if other rates are known. We can find the rate of change of the volume if I know the rate of change of radius and height, and of course for a given height and rate, radius, not rate. All of these will be known. Okay, so in this sense, we say that the rate of change of volume is related to, and hence the title of this section, related rates. So the volume, or rather the rate of change of volume, is related to the rate of change of both H and R. Okay, let's take a look at another example. Okay, so let's begin by the exercises in your book. In this segment, I'm going to do a couple of problems here for you. Questions 1 through 6 reads, an equation relating the variable x, y, and values of x and y, and the value of either dx dt or dy dt at a particular instant of time are given. We want to find the value of the rate of change that is not specified. Okay, so let's begin with exercise number 4. So in exercise number 4, the equation is y squared plus xy plus x squared minus 1 equals 0. Notice how we have the implicit form. Remember, the implicit form of the equation is f of xy equals 0. Implicit. And that was the subject of our previous section. So we need to do implicit differentiation in this one, in addition to working the related rates. Now, we are given, we want to find the rate of change of dx dt, right? That's the question mark. What is dx dt? The instant when x is 1 and y is -1, dy dt at that time, at that moment, and that instant, when those are the coordinates, y is changing at the rate of -2 units per unit of time. Okay, and we want to know what is, of course, dx dt. So let's take the derivative. Now remember, when we take the derivative, we have to do it implicitly here. And all of these, in fact, x is a function of t, and so is y. So both derivatives involving x and y will have dx dt and dy dt in them. So let's do this. Now, derivative of y squared, that would be 2y. Because y is a function of t, therefore the next step is to write this as dy dt, right? That's consequence of chain rule. And next one, that's going to be the derivative of xy. Here we got to use the product rule, right? So I'm going to write plus derivative of first 1 times dx dt, right? Remember, because x itself is a function of another variable, dx dt times y. That's derivative of x times y. Plus x times derivative of y is 1, and then dy dt. Plus derivative of x squared would be 2x, and then of course dx dt equals 0. Derivative of -1 is 0. And there we have this one. So now we can actually, let's see, we can combine like terms here. So I have dy dt, true. So for this one is going to be, let me factor dy dt. So we want to find dx dt, right? So we have dx dt here and dx dt here. Okay, so let me factor actually dx dt, because that's what we want to isolate. So that's going to make it y plus 2x, right? Y out of this one, 2x out of the last term. And then let's take dy dt to the other side. So that will change sign. It becomes -x plus, let me put them together like this. They go to the other side, right? Become negative of x plus 2y, and then dy dt. True? And that's what we have. And then we can divide dx dt. We can divide both sides by y plus 2x. So this becomes negative of x plus 2y divided by 2x plus y times dy dt. So this becomes like the general formula, right, for dx dt. Now, we're going to put what's given, what's known into this statement. Dx dt is going to be the instant x is 1, y negative 1, and dy dt is negative 2. That's going to be negative of, again, x is 1, y is negative 1. 2 times negative 1 divided by 2 times 1 plus y is negative 1. And then dy dt is negative 2. That's times negative 2. And there we have this one. And this is going to be equal to negative of 1 minus 2 is negative 1 in the numerator. In the denominator, 2 minus 1 is 1 times negative 2. 3 negatives multiply to negative. The answer is negative 2. So dx dt also turns out to be coincidental, that it's the same as dy dt. But that is the answer to this exercise. Okay. Let's take a look at another one. The other one was number 6. In number 6, negative 4x cosine y minus pi tan x equals 0. Okay, and then I'll check out those given information later. First, let's find the derivative, and then we plug in for those known quantities. Pi tan x equals 0. Okay. Again, for this one, what do we want to solve for? We want to know what dy dt is given dx dt. Okay. So let's take the derivative. Again, we're going to use the product rule in 4x times cosine y. Remember, in this section, because all of these variables are stated in terms of yet another variable, such as time t, therefore we need to use chain rule with every derivative, whether it's x or y. So we're going to do constant multiple. Derivative of x is 1, dx dt, because x is a function of t, times cosine y, plus first times the derivative of cosine is negative sine y, but then we have dy dt for that also. And then minus pi, let me close that bracket. Okay. And then negative pi, that's a constant. So we can do a constant multiple, and derivative of tangent is going to be what? Secant squared, right? Secant squared x, and then we have dx dt. Derivative, of course, constant 0 is 0. Now remember, we want to solve for dy dt. So let's group our dy dt's and dx dt's together. The only dy dt is this one, right? So I'm just going to put negative x sine y dy dt. Okay, for this one. And equal, let's take those to the other side. So pi secant squared goes to the other side. It becomes a positive. Oh, yeah, it's going to become positive pi secant squared x dx dt. And of course, the upfront 4 becomes negative 4. There's the 4 distributes to this also. So it's actually negative 4x, right? The 4 distributes to that also. Now, negative 4 cosine y on the other side, and then we have dx dt. Okay, and there we have this one. So far, so good. Now, next step, we're just going to have to factor dx dt from the right side and divide by the coefficient of dy dt. So doing so will make it dy dt is equal to factor dx dt. So this becomes pi secant squared x negative 4 cosine y times factor dx dt divided by the coefficient of dy dt is negative 4x sine y. True. Now we can move the negative from the denominator onto the numerator, and that will give us the general statement. So dy dt therefore is 4 cosine y negative pi secant squared x, all of that divided by 4x sine y. I move the negative to the numerator and distributed it over to the binomial. And then of course we have dx dt here, and again this is a general formula for the derivative at any given time for any given coordinates x and y. Now we were told that if x is pi over 6, right, in the exercise we had x was pi over 6 and so was y, and we were given dx dt. This is all given in the problem, see, right up here. This is all given up here. So given those, we want to find dy dt, and all I got to do is plug in for x, y, and dx dt in there. So it's not bad if you're given the equation, but as you will see later on, the challenge here is to, for a given word problem, we need to come up with the relationship between these variables ourselves, and that's going to pose a little bit of challenge to us. Okay. Cosine y, cosine of pi over 6, that's cosine of 30 degrees, right? Which is root 3 over 2. And then negative pi secant of 30 degrees. That's going to be, secant is 1 over cosine. It's cosine root 3 over 2. So it's 2 over root 3. Okay. And then we square it because it's secant squared. Divided by 4x. X is pi over 6. And sine x, that would be sine of 30 degrees, which is 1/2. And dx dt is 1, right? That's dx dt. So I didn't forget to multiply it by 1. But it's not going to change the right side, but nevertheless we have to do that. Now let's tidy up this fraction. In the denominator, the easier of the two, well, 2 times 6, 12, 4 divided by 12, that's 1/3, so it's going to be pi over 3, right? And in the numerator, you distribute 4 times root 3 over 2, you get 2 rad 3 negative. And this would be 4 pi 2 squared divided by root 3 squared is 3. And let's multiply top bottom by 3 to get rid of the complex fraction here. And I'm just going to put the answer down. So dy dt is going to be, in the denominator, I'm just going to get pi. In the numerator, I will get 6 rad 3 negative 4 pi. So that's the rate of change of y with respect to t for given conditions. Okay, let's take a look at another exercise. In exercise number 16, the question reads, a race car is moving along a track described by the equation. And there you go. Notice that equation, by the way, is not a function. You do your vertical line test, it fails almost everywhere, right? Except at 0, -2, and 2. And even at those points, you have vertical tangent, but still. So anyhow, this isn't a function, but it's a relation or just an equation. Where both x and y are measured in miles, how fast is a car moving in the y direction? That is dy dt. When dx dt is -20. So in other words, the position of the car in the x direction, in the horizontal direction, is changing at the rate of -20 miles per hour. And yeah, because x is in miles, we were told, yeah, x is in miles, and so is y. And speed is in miles per hour, so our unit of measurement is time, is hours. Okay, so we want to know the change in y direction in miles per hour as x changes at the rate of negative 20 miles per hour. So we want to know what the change or displacement of the car is. That's what dy dt is, right? Because y is change in direction of y per unit of time. So that's what it says. Find the speed. How fast is a car moving along that? The car is at point in the first quadrant with coordinate x equal 1. So right in here, we want to know at that point what's the speed of that automobile in that direction. So let's proceed with our differentiation. So our equation first. Remember again our assumption: x is a function of time, and so is y. Could be the same, could be different. We allow for different function of time. Okay, derivative of x to the fourth, that's just 4x cubed. But remember, in this section, you always have chain rule. For any variable, you differentiate with respect to third, fourth variable t, depending on how many variables are in the equation. Derivative of negative 4x squared, that's negative times 2x. But then again, we have dx dt. Okay, and the next one, we're going to use the product rule. Derivative of x squared is going to be 2x dx dt times y squared plus first times derivative of second, which is 2y, and then you have dy dt. So we just did product rule for these. Derivative of 4y squared is going to be 8y dy dt, and derivative of y fourth is going to be 4y cubed, and of course dy dt. Notice every one of those has either dx if it's x or dy if it's a y variable. Good. Let's combine like terms. So our dx dt's, and we want to find dy dt. So let's group dx dt's together and dy dt's together. Okay, so first dx dt's. Dx dt. Beginning with the first one. It's going to give me 4x cubed negative 8x plus 4x. Those work out nicely. And then, of course, there's a y squared. So they're not like terms. I was hoping they'd come out like terms, but they're not. And that's okay. And let's move dy dt's to the other side. So they're all positive on the left. They become negative on the right. I'm going to factor negative on the right. So it's going to be 4x y squared. And then plus 2x squared y. Oh, actually, sorry. I'm doing dy dt. So let me get rid of these. That one is in error. Okay. This one. So that becomes 2x squared y minus, which of course in parentheses is plus, 8y, and then plus 4y cubed. Right, so we have these. And then we're going to divide both sides by the coefficient on dx dt. And of course we have dy dt on the right side. Still, I need to write that one. That's dy dt. Okay, so dx dt becomes all of the right, negative 2x squared y plus 8y plus 4y cubed divided by 4x cubed negative 8x plus 4xy squared times dy dt. And again, there you go. That's the general form of the derivative. Now we're going to mine those specifics, what's given. The moment when x is 1 and dx dt is negative 20, right? So we were given those. And we're told the car is in Q1, right? So y is going to be positive. True? So when x is 1 and we are given dx dt is negative 20 miles per hour. That's the change of, that's the velocity in the x direction. We want to know the velocity. These are actually the components of the velocity. So let me just kind of give you real quick here. This is the velocity. vector, right? So we're looking at is the component velocity in the x direction. That's what negative 20 mile per hour is, right? Of course, sorry, because it's negative, let me do it realistically. So something like this, that's velocity negative 20 miles per hour, because negative means it's moving to the left, right? And there you go. And this is the velocity itself. So we're looking at this part. This is what we want to know. What is the component of the velocity in that direction? So let's plug him in. And we're going to get our dy dt. I know I solved for dx dt, but that's okay. We're going to plug in the numbers anyhow. So I should have isolated that, but that's no biggie. And for this one, let's see, when I plug it in, when x is 1, and actually here I just realized for dy dt, there is a 2 on the outside here that distributes to this. So this is going to be 4. I know, probably some of you caught that one, but let me see. That's going to be 4. Okay, now it looks better. Okay. All right. Now, here's what we need to do. Notice in our equation in here, we have both x and y combined, but we are only given x. We don't have y, do we? So we need to find y, right? How do I find y? Well, y, when x is 1, we're going to use the general equation here, okay, to find y. So that's what I'm going to have to do. So I'm plugging in again for x in the original equation. The original equation is x to the 4th negative 4 x squared plus 2x squared y squared, and then plus 4y squared plus y fourth equals 0. And then if we simplify this, we're going to get y to the 4th. Let me write that first. Y squared, we got 2 and 4, that makes it 6y squared plus 6y squared. And then the constant is negative 3 equals 0. Okay. Now, this one we can solve for y. This is quadratic in form, that is, we can either factor it or use quadratic formula. Let's use quadratic formula on this one. So if you let, for example, this is what I mean by quadratic in form. If I let m be y squared, then this is in the form m squared plus 6m minus 3 equals 0. Now, using quadratic formula, m is going to be negative b plus or minus square root of b squared minus 4ac divided by 2a. Okay, this is from your algebra, right? So this is going to be negative 6 divided by 2 is negative 3 plus or minus. The radicand is going to be what? Let's see, the radicand, 4 and 3, 12. 12 and 36 is 48, correct? 48. Yeah, square root of 48. Now, square root of 48, that's going to be what? 16 times 3 is 48. So that's just, let me just put 48 first and then I simplify it. That's root 48 divided by 2. Don't forget to divide by 2, because when you divide 2 and 6 out, the 2 doesn't go away, right? We need to keep it on the second part of that fraction. I'm splitting this into 2 fractions essentially. So it's negative 3 plus or minus. Now square root of 16 is 4. This is 4 rad 3 divided by 2 makes it 2 root 3. Now the negative, negative 3 minus 2 root 3 is going to be negative. And negative 3 plus 2 root 3. Root 3 is about 1.7, so this is 3.4 minus 3, that's positive 0.4. We're going to rule out the negative answer. Why? Because we were told the car is in the first quadrant, right? In Q1, so we're only going to accept the positive value in Q1. So the value of y, in other words, we found it. I'm going to add it on to what we have up here. Negative 3 plus 2 rad 3. So this is what y is. Negative 3 plus 2 root 3. That's what we found it to be. Now we can plug that in actually, right? Oh, actually, sorry, we can't do that yet. I'll fix this. And here's why. I solved the equation for m. We need to solve for y, don't we? So we need to take the square root of this number. Therefore, because y squared is equal to m, so y would be plus minus root m. And our m is, so this is going to be plus or minus negative 3 plus or minus 2 root 3. This is interesting. Now let's decide how can this be positive. And of course I have the square root of it, right? It's the square root of that. What a mess, huh? Again, the negative is out because y must be positive, so negative root whatever plus minus 2 root 3, this is going to be out because that's going to be negative, right? We need y to be positive. So we're going to accept actually y is going to equal to square root of negative 3. No, we have plus or minus 2 root 3. We need to resolve that also. If I go with negative 3, square root of negative 3 minus 2 root 3, right, negative 2 rad 3, this expression is going to be negative. You have a square root of a negative number. This is not real, right? We get into an imaginary situation. So the only acceptable answer for y is therefore square root of negative 3 plus 2 root 3. And that is the y that we actually need. Okay, so it's 2 root 3 minus 3. And up here I'm going to put a radical on there. That's what y is. Now we are in a position to do dy dt, and boy, this is not going to look nice, but let's try it anyhow. Let me move things south. Remember, we're now plugging in all of the numbers into that expression. Okay, so this is going to be dx dt is equal to negative parentheses 4 times x is 1, x squared, so that's 1 squared. Y is times, you know what, I need more room. I can see this being messy. Yeah, I'm gonna move way down here. So let me copy this maybe down and then I'll come back. Okay, so let's continue on with this one. What I've done, actually, I've done all of the legwork because a lot of detailed work from here on out. So I just want to make sure that I did all the dirty little details, and then that way I don't take up too much of our lecture time. It makes the lecture too long. So what I did is the following. I copied the formula. These two pieces I copied from a step above. Okay, and then I went ahead and plugged the numbers in. So it's direct substitution for x and y. I put in 1 for x, and the radical negative 3 plus 2 root 3, I plugged it in for y. And then the rest is just algebraic simplification. So what I did in the numerator, well, everything in the numerator and denominator, I saw that there was 4 in common to all of them, so I divided the 4s out. And that reduced the numerator to what you see in here. Okay, the first two radicals, these two ended up being like radicals, so I was able to combine them into one, and then also this one is cubed, so that's also in here. Let's see, this should have been actually, yeah, that looks right. Okay, so I got, again, like radicals. I had 2 up here and 1 more. That makes it 3 like radicals, and that's how I got this one. Okay, and once I did that, this was 2 and this is 1. Once I did it, I combined it with the square root of 2 root 3 minus 3 cubed. That's that part. And then divide by, in the denominator I have 1 minus 2. Those combine into a negative 1. Correct? That's how I got the negative 1 down here. And then when you square the square root, we're going to lose the radical, so I just have 2 root 3 minus 3, which is the radicand. That's what's down here. Okay. And then, what did I do next? Next, I factored square root of 2 root 3 minus 3 from the numerator. So factor it from that expression. That's how I got the 3. Okay, and then factored 1 from the numerator. So that leaves me with the square root of 2 root 3 minus 3 squared. And with that, I lose the radical. I just get 2 root 3 minus 3. And that's how I got the denominator. That's what I have over here now. And then once I did that, I combined like terms in the denominator. Negative 3, negative 1 makes negative 4. That's how I got this negative 4 down here. And in the numerator, once I factor the square root, you kind of see how that works out. Inside parentheses, I have 3 minus 3. They're opposites. And next step, what I did, because we need to solve for dy dt, so I crossed out the negatives actually here, right, and multiplied those together, just like cross multiplying. I multiplied 20 times the binomial in the denominator, and of course in the numerator everything's still there. Move 2 root 3 to the front. Okay. And after I did that, I multiplied by the radical. And in the next step, I isolated, I divided both sides by that expression, the coefficient on dy dt. And worked it on the calculator and got negative 4.5 miles an hour. So that just means the movement is in the negative direction. So at that point, again, the car is moving in this direction. The component of the velocity in x, velocity in y are both negative. Moving to the left, and the component of y is in the negative direction, means downward. And then I projected it onto the original sketch right in here. See, that's kind of how it's going at that point. And because of the velocity, that the way it turned out, both x, y negative means moving in that direction. That tells me that this should be the direction of motion of this moving car. Okay, so there you have it. Again, rather elaborate example of related rates. Let's work on another example. Okay, let's take a look at exercise number 18. In exercise number 18, we have a 20-foot ladder, leaning against the wall, begins to slide. How fast is the top of the ladder sliding down the wall at the instant of time when the bottom of the ladder is 12 feet from the wall and sliding away from the wall at a rate of 5 feet per second? So let's do a sketch of this one. I really find this sketch useful, and I encourage you to really do that. Otherwise, this is going to be difficult to imagine the geometry of it. You got to do everything in your head. So here's the wall. Okay, it's leaning against the wall. There's a 20-foot ladder, so I'm just going to put a 20-foot ladder here. Okay, now it begins, the bottom of the ladder begins to slide in this direction, right? And we are given the rate is 5 feet per second. Now that's the change in the horizontal distance, right? So the fact that it's a rate, that means that should be a rate of change. That's dx dt because it's in a horizontal direction. And that dx dt is going to be 5, right? Okay, so dx dt is 5. We want to know the instant x, the ladder is 12 feet from the wall. So when this distance is 12 feet from the wall, how fast is top of the ladder sliding? We want to know what dy dt is, right? Now the instant the ladder is, the base of the ladder is 12 feet from the wall, because the length of the ladder is a fixed length, right? What's changing is the x and the y. So the moment x is 12, the ladder is 20. What is y? Well, we can do the Pythagorean identity for this one. We get 20 squared equal 12 squared plus y squared. That's 400 minus 144, and that's 100 and or 256, right? 256, that's equal to the y squared. So y is going to be square root of 256, or that's 16 by 16. Okay, so at that point, this distance is 16 feet. Okay. All right. Now we need an equation that brings x and y together, right? Because we have dx dt. We want to know what dy dt is, right? The way the question is asked. Again, the question reads, how fast is top of the ladder sliding down? There you go. So how fast, that means rate of change of vertical distance over unit of time. That's the definition of how fast, rate of change of position with respect to time. And we are given when x is 12 and at that time y is 16. See, it's just like the earlier problems we did. Now, the equation that brings x and y together, in general, we can get that from the geometry of this problem. Again, this is at any given time, that's x, y, that's 20, right? That's how the x and y are related together. So we can say, using Pythagorean theorem, x squared plus y squared is 20. That's the equation that we need. Now, let's take the derivative of both sides. Derivative of, again, x here, the horizontal distance is a function of time as it begins to slide, and so is y. So anytime we take the derivative of x and y, we're going to have dx dt and dy dt respectively. So derivative of x squared is 2x, but remember dx dt, chain rule. Derivative of y squared would be 2y, and then dy dt, its own chain rule, and 0 on the other side. Okay. Now, we want to know what dy dt is, right? So we can solve for dy dt, and dy dt is going to be negative of x over y dx dt. Just isolate. You can divide the 2's out and then isolate dy dt. That's what we're going to get. And we're going to plug them in, the numbers that we need. So it's going to be negative of x. X was 12. And the y is 16. dx dt is 5. And this is going to be 60 divided by 16, right? Or 3.75, right? 60 by 16, negative 3 3/4, 3.75, which means it's sliding down at the rate of that feet per second. Remember, a negative, how do we attribute a negative in a velocity? How do we justify? That means a direction. That means it's going in a downward direction. It is a sliding downward. So that is, that's how we know. the negative sign. That's the interpretation of the negative velocity. And we are good to go with this one. Let me do another one. Okay, let's take a look at number 30. In number 30, we have two ships leave the same port at noon. So let's say they're here at port. This is at 12 p.m. Ship A moves north at 18 kilometers per hour and ship B moves northeast at 20 kilometers per hour. How fast is the distance between them changing at 1 p.m.? So let's see. At 1 p.m., ship A moves north. So it's over here now. This is at 1 p.m. How far has it gone? How far has it traveled at 1 p.m.? Well, it's been 1 hour into its journey, and it's going at 18 kilometers an hour. So it has moved 18 kilometers away from the port. That's where ship A is. Ship B is the faster one at 45-degree angle. So let's say it's going over here. And this is where ship B is going to be at 1 p.m. At the same time. How far has it traveled? Well, it's doing 20 kilometers in an hour, right? Per hour. So in 1 hour, it must have gone 20 kilometers from the port. We want to know how fast. Again, it's fast. That means rate of change of distance per unit of time, speed. How fast the distance between them is changing at 1 p.m. Well, the distance between them is this distance, right? Call it capital D for distance between them. How fast we want to know the distance between them changing. Now, the way they work the angles, we are given this angle is 45 degrees. Okay, so we need again an equation that joins, call this the distance A travels. I don't know, let's use X and Y for these. And we need an equation that joins X, Y together and D distance between them. And because this is a triangle, we got to look at the triangle relationship, right? So the triangular relationship we're going to look at is, let's see, this, we're going to have to use the law of cosines, right? The law of cosines to find the relationship between the three sides. That's why we use the law of cosines. We were given three sides, we want to know relationship between them. Notice I cannot use Pythagorean because the angle between them is not 90 degrees. So we have to use the law of cosines. Using the law of cosines, let me write that, law of cosines, we're going to write d squared is equal to x squared plus y squared, negative 2xy cosine of the angle between them, but the angle between them is fixed 45 degrees, not changing. So we're just going to put 45 degrees there. Okay, now we can actually take the derivative and find the rate of change of distance between them. Now, notationally, the question they ask, how fast is the distance between them changing? We need to show that notationally. That's dd, dt. That's why I use cap D, because you have dd. This would be the rate of change of distance between the two ships at 1 o'clock, at that instant of time. Okay, now let's take the derivatives here. Okay, so when we take the derivative of d squared is going to be 2d, and then of course dd dt, and that's good. That's what we want to find. And while we are at it, let's find actually the distance d between them at 1 o'clock. So at 1 o'clock, this is kind of how this is going to look like. There you go. This is how things are at 1 o'clock. This distance is x. Now at 1 o'clock, remember, this is 18 and this is 20 because that's how fast they go in an hour. We want to know what d is, and this angle is 45 degrees. So I can use the law of cosines. D is going to be the square root of, using the law of cosines, square root of x squared plus y squared, negative 2 times x times y times the cosine of the angle between them. Okay, and the square root, I worked that one. The square root turns out to be 214.8831. And that square root is actually about 14.60. There you go, 14.659 kilometers. That's how far apart they are. Okay, and because that's for 1 hour, actually, that should end up being the answer to the question, ironically. Okay, well, let's go through and see. This is how far they are apart from each other 1 hour into it. And if you look at the rate of change per unit of time, so it's going to be 14.66 kilometers per hour. But let's go through the motions anyway. The derivative of x squared would be 2x, but then remember dx dt. Derivative of y squared, 2y, dy dt. And then negative 2 times, in fact, cosine of 45 is 1 over root 2. Let's do that one. Now, xy, derivative of xy, we're going to use the product rule. That's derivative of x, dx dt, times y, plus derivative of y is dy dt, times x. So I did derivative of first by second plus derivative of second by first. Okay, we're good. Now we need to isolate dt, right? We want to know what the rate of change between them is, which I already know the answer is right in here, but that's okay. They could have given us let's say 3 hours into it, so we have to go through this motion for something other than 1 hour. Now if you know that everything has 2 in it, right? All the terms have 2 in them, so let's cross out the 2's. Therefore dt is going to be the right side, which is x dx. Let me see. I'm going to factor dx dt. I have dx dt here and dx dt here. Let's factor dx dt. So dx dt turns out to be x and negative 1 over root 2 y plus, let's do dy dt. This is dy dt and there's dy dt. Don't forget to distribute 1 over root 2. So factoring now dy dt, that's going to make it y minus 1 over root 2 x. Okay, and then divided by d, and we just found d, correct? But the general form, since I haven't put any numbers in, d is going to be square root of x squared, y squared, negative 2xy cosine 45, to keep it general. So this will give you the rate of change of distance between them after 1 hour, 2 hours, 3 hours, any time after that. What about a day later, 2 days later, and so on and so forth? So we can do this. Now we're going to make this work for 1 hour. Okay, so at 1 p.m., an hour into again this journey, dx dt, well, dx dt is how fast ship A is moving, right? That was 18 miles an hour. And then x is how far it is from the port in 1 hour is 18 kilometers. Sorry, everything is in kilometers here, not miles. So used to miles because of what we use. Okay, and then I have 1 over root 2. Y is going to be 20 kilometers. dy dt happens to be 20 kilometers per hour. 20 kilometers away in 1 hour minus 1 over root 2. Ship A is 18 kilometers away from the port. Divided by, and I did d here, right? So let me just use that so I don't have to rewrite the whole thing. 6589. All right. And working the arithmetic of this fraction, the numerator ends up being the first part. I got it to be about 69.4416 plus the second parentheses times 20 end up being 145.4416 divided by denominator, which is 14.6589, and that's going to be 14.66 rounded. Notice I knew that's going to be the answer because we found everything an hour into this. That's how it's changing, the way they give us the information. But this is a rate of change, so this is kilometers per hour actually, right? It's per unit of time, which is an hour, the unit of time here. And there we have it. We are done with this one. Let's take a look at one last one here. Let's take a look at this last exercise from this section. This one is kind of interesting, especially the geometry of this, how it's going to turn out. The question reads, shortly after taking off, a plane is climbing at an angle of 30 degrees and traveling at a constant speed of 600 feet per second as it passes over the ground radar tracking station. At that instant of time, the altitude of the plane is 1,000 feet. So that's directly when the plane is directly above the radar, that distance. So don't be misled with this picture. It's sometime later. So we really don't presume like we don't even have that for the moment. We want to know where things are happening directly above the radar. Notice we don't have a triangle at this point, so we need to create a relevant triangle in just a moment. At an instant of time, the altitude of the plane is 1,000 feet. How fast is the distance between the plane and the radar station increasing at that instant of time? Right? When the plane is at this point. So what I've done is I actually transferred that image over here. And so this distance is actually right in here. That distance is 1,000. So that's where the plane should have been. That's 1,000 feet. 1,000 feet. Now I'm looking at sometimes before the plane has reached directly above the radar. So some t prior to this, the plane must have been here, and then the plane is going in that direction, right? And it continues on at a speed of 600 miles per hour. Now, the distance that's changed between the plane and the radar at any given time is actually this distance, right? We call that d. So that's what we want to know, the rate of change of distance, the instance the plane is directly above the radar. Now let's translate the angle here in our work so we can complete our triangle. So this is distance, horizontal distance, call it x, from here to here. Okay. And this is the angle, 30-degree angle. And let's see. At that time, whenever the time, some t again, before it reaches the altitude of 1,000 feet directly above the radar, this distance is going to be y. And what's left over is going to be 1,000 minus y, because directly above the radar, the distance, the altitude is 1,000. Okay, and we have this angle is 30 degrees, so we need this side. We have x, y, whatever we want to call that. We can call it z. Okay, now let's come up with our equations here. And what we want to know is this. The question, what was the question asking? dd dt, right? That's what we want to know. But we need to write it in terms of an equation that relates d with other variables. So from this triangle, we can say that d squared is equal to x squared plus y squared, right? Pythagorean, because this is a 90-degree angle right there. Okay, that angle is 90 degrees. So in this triangle, that's the relationship. Now, we need to somehow, because what's changing is actually the direction of the airplane, the speed of the airplane. How can I relate that to some kind of a d of something over dt? So what's changing as the plane moves from one point to another point to another point? You see that? That's the fixed rate of 600 miles an hour. That's the change in z, the direction of the plane, right? The distance of the plane from where it was a few minutes ago, where it is at now, where it will be a few minutes from now, right? So we are given the speed of the plane, we translate it into dz dt, that's 600 miles an hour. Okay, now I need to relate capital Z, this Z, capital lower, doesn't matter, this is Z, and find the relationship between, or somehow put Z inside of here in that equation that we have. Okay, so now let's take a look at this triangle. This is 30, that's Z, and this is 1,000 minus Y, and that is X. So in this triangle, if I look at, for example, sine of 30, that's opposite over the hypotenuse, and that's 1/2. Sine of 30 degrees is 1/2. So I can cross multiply here, and I get Z is 2,000 minus 2Y. Okay, or we can say that, well, we can solve for Y actually, because we want to see in here, I want to go in with Z in there because I'm given dz dt. So Y is equal to 2,000, bring it to the other side, becomes negative 2,000, divide both sides by negative 2, it becomes 1,000 negative 1/2 Z. So now I can write Y in terms of Z. So keep in mind though, at when Y is 1,000 feet, this becomes 0, right? Z is 0, which makes sense. That's exactly the time when the plane is directly above the radar. Okay, so that Z is going to be 0. Okay, and at that point, actually, D, the distance between the plane and the radar is 1,000 feet, and at that point X is 0, right? This is all happening at when the plane is directly above the radar, and you can verify that against our graph. X is 0 because the aircraft is directly above, so X will become 0 there. Okay, we're good now. The other thing I need is the relationship between X and Z. We have it between Y and Z. We need it for X and Z, and here actually in this triangle, let's look at cosine of 30 degrees. Cosine is adjacent to hypotenuse, so from this we get X is equal to Z cosine 30, and cosine of 30 is root 3 over 2, so it's going to be root 3 over 2Z, right? So we're able to write both X and Y in terms of Z. Okay, which again ties in with dz dt, the speed of the aircraft, in just a moment. I think we're good to go. Let's actually do this then. Let's change our equation. D squared is X. Remember, X is right in here. X is root 3 over 2Z. So I'm going to write X squared as root 3 over 2Z squared, plus Y was 1,000 minus 1/2 Z squared. The hardest part here is the geometry and coming up with the relationship between the variables. That is, this equation is the hardest part. Once we have that, the rest will be easy. So now let's take the derivative with respect to t. We want to look at the changes between all of these over time. derivative of d squared would be 2d. Then we have dd dt equals square root of 3/2 is squared. That's just 3/4. And then derivative of z squared, right? Because z is a squared. That's going to be 2z. And dz dt, there you go. And that's how the speed of the aircraft comes into this. And plus derivative, the power rule here, derivative is going to be 2 times 1,000 minus half z. That's the power rule, the outside function, inside function, negative half z. The derivative of negative 1/2 z is negative 1/2. And of course, chain rule, that's dz dt. Okay. Now let's tidy up this work. So on the left we have 2d dd dt. Okay. And now to the right, let's see, dz dt, dz dt, and okay, if you distribute this to both terms, okay, distribute this expression, I have negative times negative is positive. This is 1/4, right? And then, oh, actually, let's divide all the 2's out. What do you say? Yeah, we can do that. 2, 2, and 2, dividing all the 2's out. So now I have half and half makes 1/4. That's 1/4 z dz dt. And then I have 3/4 in here of z dz dt. See, there's z. So 1/4 and 3/4 makes a whole, right? So I have just z dz dt, right? 1 whole z dz dt. So that gets rid of that part. Now, distribute. So remember, we accounted for this. It's combined now with this part of the product. And then distribute, again, this expression to 1,000. So we're going to get negative, 500 dz dt. So it reduces very nicely, actually, which is good. It means we're doing it right? When things go in the right direction. Now, so this is what we have, and we can factor dz dt if you like, dz dt, and that's going to be z minus 500, and that's d dd dt, and finally our dd dt is going to be z minus 500 over d times dz dt. So there's our equation that we usually find. Now we're going to make this work for specific details. For the instant the aircraft or the plane is directly above the radar. Okay, so let's plug that in. Z, remember, we have it right in here. Z is going to be 0 at that point, right? When the aircraft is directly above the radar. So that's negative 500. D at that point, again, D, we just agreed that's 1,000. That's exactly how far the distance is between aircraft and the radar. And dz dt, that was the speed of the aircraft, which is, we're going to take that to be 600. Right? And let's see. So there we have that one. And that's it. And then we can actually work this. The zeros turn out, we get 300 feet per second. That's how it's changing. Now let me see something here. Okay, what I was looking at was, because this becomes a negative quantity, so here's how we're going to make this work, because everything looks good. I'm going to make this negative 600 dz dt. Okay, so let me write that. dz dt is negative 600. feet per second. And the reason is because we want to make sure that the velocity here turns out to be positive. The speed turns out to be positive. So otherwise, because we don't have a reference to a direction here, right? We just want to know how fast the distance is changing, right? So that would be the justification for making this change positive. So we're going to take the speed to be negative 600 feet per second. So there you go. Now we can change that, like how fast is it in terms of like miles per hour. Well, if I go through my conversion formula, 600 feet per second, well, there are 5,280 feet for each mile. So I want to know what it is in miles per hour. That's just me. The question didn't ask that. And here we have seconds, right? So there are 60 seconds to each hour. See how I line these up so I know how to come up with the answer. And actually 3,600 seconds, right? Sorry. There's 60 minutes to an hour. 3,600 seconds to an hour. Okay, so that means I got to multiply 600 times 3,600 divided by 5,280. Okay, and when we do this on my calculator, I get about 204 miles per hour. So the answer is going to be, again, in feet per second. That's what the answer turns out to be. Make sure I answer the question. How fast is the distance between the plane and the radar increasing? The distance is increasing. Okay, so that's why, again, we need to turn this rate into a negative rate so we get a positive rate of change of the distance here. Because it's distance, right? This is the rate of change of distance increasing. We're going to have to we're going to make this to be negative 600. Otherwise, it won't make sense to have negative 300 for increasing. Okay, and with that, we are done. We are done with this exercise, and we are done with the section. So we did quite a few examples here. Now, think of this as the application section of derivatives that we've done. So, again, very interesting. We did quite a few applications and the topic of related rates. And with that, we are done with this section.